Okay, well, it's for me a great pleasure to introduce Calvin Pfeifer from Köln, who will speak about the generic representation theory for valued quivers. Thank you, Calvin. Please.
Thank you very much for the invitation and giving me the opportunity to speak in your seminar. Yeah, I will talk about the generic representation theory of valued quivers. And so first I should say what I mean by generic representation theory. So this is related to the geometry of representation varieties. And since we are doing geometry, it's much nicer to assume that K is an algebraically closed field throughout the whole talk, which for simplicity has characteristic 0. So that's fixed throughout the whole talk. And then we consider finite dimensional algebras. Oops. Okay. Sorry. We consider finite dimensional algebras A given by bound path algebras. So Q is always a quiver, and I is always an ideal. And this should be a finite dimensional algebra. And then given a dimension vector D in the free abelian group generated, or the free monoid over the positive integers generated by the vertices of our quiver. So this is a dimension vector. And to this, we have associated a variety of representations of A of dimension D. And this is just the collection of all matrices. Let's call such a collection V, which is just a tuple of matrices, one matrix for every arrow in the quiver. And that's a matrix of the size corresponding to the dimension vector. So this should be then of size D at the target of my arrow A times D, the value of the dimension vector at the source of my arrow A, such that all the relations coming from the ideal are satisfied. So if I plug in the matrices corresponding to the arrows of my quiver into a relation from the ideal, then this should be annihilated. So this gives some polynomial equations in the entries of these matrices, and we just consider the affine variety cut out by these polynomial equations. Yeah, so this is an affine variety, and on this variety acts a group, namely the general linear group, corresponding to the dimension vector D, which is defined as the product of the usual general linear groups at every vertex, so of size di for any vertex I in the quiver. And then one can phrase representation theory as the problem of classifying GLD orbits in the representation variety, meaning we may take a representation in the representation variety and then associate to it an orbit O of V, which is just defined as GLD applied to the representation V. Yeah, and how does, I mean, maybe I didn't say how the general linear group acts. It acts by conjugation on the matrices, of course. So this is a subset of rep AD again, which we call the orbit. Maybe I should mark what we just defined here. Okay, and then we note that GLD orbits they correspond bijectively to isomorphism classes of representations of the algebra of the finite dimensional algebra A with dimension vector D. And our goal, our overall goal in, let's say, yeah, maybe geometric representation theory, at least from this perspective, is to classify or to understand representations of our finite dimensional algebra A generically. And that means more or less two things. Namely, we want to understand the irreducible components of all the representation varieties for all dimension vectors. And second, we want to understand the generic properties of, let's call such irreducible components Z of each of these irreducible components. And maybe I should also say what I mean by a generic property. So a property, let's say curly P of elements of Z is or holds generically if there exists an open subset U of the irreducible component Z such that the property P holds for all elements of U. Okay, so that's generic representation theory, and that's the overall goal. And of course, this is way too general in this setting. So what I would like to do today is to focus on a particular class of algebras coming from valued quivers. But before we pass on to this very nice class of algebras, are there questions about this general story?
No.
No? Okay, perfect. Then let's pass on and get a little bit more concrete, namely to valued quivers. So what do I mean by a valued quiver? A valued quiver gamma consists of several data, namely a set of vertices gamma 0, the set of half edges gamma 1, an orientation omega, a valuation u, and a symmetrizer sigma. Okay, I'll say again what all of these words mean. So this is just, as for an ordinary quiver, this is just a set of vertices. And then we have gamma 1, set of what I call half edges. So this is gamma 1 is a subset, is itself a subset of the product of gamma 0 with gamma 0. So if we maybe label the vertices by I and j, let's label two vertices by I and j, then this tuple gamma 0, gamma 1 should describe a simple graph. So we have that edges between I and j are given by pairs of half edges in gamma 1. Yeah, so gamma 1 gives you somehow these two half edges. Maybe I don't want to get into the formal definition. I'll just keep on drawing the picture, and then it should be clear what I mean by a valued quiver. On the other hand, we have omega. This is what I said, or what I called an orientation. So this itself is a subset of half edges, which somehow chooses for every such edge, as here on the right, the tip. So it chooses one of the two compatible half edges and calls it the tip. So that's then that gives you an orientation. And then we have here, this is what we've called a valuation, this new. And that's a function from every half edge to the positive integers. So it assigns to every such half edge here an integer new ji, and to the other half edge another integer new ij. And finally, we want to have also a symmetrizer. So sigma is a function from now the vertices of my valued quiver to the positive integers. So it assigns here to every vertex j a value sigma j, and to I a value sigma I. And it's called symmetrizer because it has to fulfill the following equality: sigma I times new ij is equal to sigma j times new ji. So if you take these cross products here, then these cross products should be equal. Okay, so that's a valued quiver. And yeah, maybe let's see some more concrete examples maybe. Of course, first of all, every 2 acyclic quiver so by 2 acyclic, I mean it does not have any loops or oriented cycles. Every 2 acyclic quiver gives us a valued quiver by just taking new ij to be equal to new ji, and this is defined as the number of arrows from I to j in Q. Sorry, from j to I, or from I to j in Q. Then second example, which does not come from an ordinary quiver. So that's let's consider this one. So we take let's say it's linearly oriented. It looks like linearly oriented type A quiver, but now we add some valuation, some non-trivial valuation. Namely, at this end we put 1, 2, and at this end we put 2, 1. Then this, and whenever I draw an arrow without valuation, I mean that both valuations are equal to 1. So this is called a valued quiver of type Bn tilde. Then another example would be you can kind of draw a very similar valued quiver. But this time we put the 2 to the outside and the 1s inside. And then we obtain what's called a valued quiver of type Cn tilde. And yeah, maybe you can also, I didn't mention the symmetrizer, but in this case, it's easy to work out the symmetrizer. So the symmetrizer in the type Bn case would be 1, 2, 2, 2, 1. So 1's on the outermost vertices and 2's at the innermost vertices. And here in type Cn, it would be 2, 1, 1, 1, 2. And then maybe a fourth example.
Excuse me, Calvin, I didn't understand what happens in the arrows in the middle in those previous examples.
So the middle, okay, maybe I can.
All of them are.
The evaluation is 1, 1, right?
Yes, exactly. I just said this orally, but I should also write it down. So here the valuation is actually 1, 1, 1, 1 everywhere. And whenever both valuations are equal to 1, I just drop them and don't write them at all.
Excuse me, is it possible to think of valuation as just some rational number, just some, well, if
No,
multiply them by something, like nothing changes?
maybe it is indeed, it does make sense to think of them in terms of rational numbers. If you multiply both, well, not quite, not really. No, actually not. So this bar in the middle should not be confused. The notation does not suggest or shouldn't suggest that it's like a ratio.
Oh, I see. Yeah, yeah. I was kind of confused by this sigma times v is v times sigma thing. So if you like
no.
multiply valuations by something, then
Yeah.
like nothing changes. The condition
Yeah.
still.
Yeah. Okay. Yeah. But I think it really matters whether you multiply. I mean, it really changes a lot the representation theory if you multiply both by some fixed integer. Other questions? No? Then yeah, let me quickly do the last example, which again looks very similar to the examples before, but this time we put once a 2 outside and once a 1 outside. And now the symmetrizer gets a little bit more complicated. Namely, it's 1 here, then it's 2 from there on. And in the end, it's actually 4. And this is then called, sometimes called type B, C, N tilde. Okay, so now you have seen some valued quivers, and I at least sketched a more formal definition, and I hope you will now kind of at least recognize a valued quiver whenever they come up. But we want to do representation theory. Yeah, so this was only combinatorial. Let's now do representation theory. So for this, we have to associate to a valued quiver an algebra, namely the GLS algebra. And this GLS algebra is often denoted by H, and it actually depends on a valued quiver, so one should actually write H of gamma. And this is just given as a path algebra modulo some ideal. So what do? We start with our valued quiver gamma, which looks locally like before, ij, nu ji, nu ij, sigma j. And then we associate to this a quiver Q, and this was done by Geiß Leclerc Schröer. That's what the abbreviation GLS stands for, Geiß Leclerc Schröer, in 2014. So they defined a quiver, and what they do, they still take locally these two vertices I and j, but then they put a bunch of arrows in between I and j, and they put a loop at every vertex. So we call the loop epsilon, it loops epsilon with index given by the vertex, and then we have a bunch of arrows which we call alpha ji, and well, there are many of those, so from alpha jy1 up to alpha ji to the g ji, and this yeah, the number g ji, this is given by the greatest common divisor of nu ji and nu ij. Yeah, so yeah, some rule to remember this. We somehow, from the valued quiver, we put as many arrows between the vertices as the valuation allows us to do. Yeah, okay. And then, so that's the quiver. But of course, this is a very, very wild thing. So we should better add some relations I. And the relations I, this ideal of relations is generated by commutativity relations, which are of the form epsilon j to some number fij, which I define as, in a second, alpha ji, for any such arrow alpha ji minus alpha ji, any such arrow, and then epsilon, and then first applying epsilon to the fji. So I should say what this fji is, or fij. So fji is defined as take the valuation nu ji and divide by the greatest common divisor, gji. Okay, so these are the commutativity relations. And then there are also nilpotency relations. So epsilon I to the sigma I, the value of the symmetrizer at I, should be 0. Okay. Yes, please, the question? No?
No, I was just saying yes.
Ah, okay. Okay, cool. Yeah, so and this now defines our GLS algebra. So actually, once you worked a little bit with this valued quivers, it's not too complicated to cook up the algebra from the valued quiver. Yeah, let's maybe see immediately an example to make it a little bit more down to earth. So as an example, let's take the valued quiver gamma given by 1, 2, 3, 1, 2, 1, 2. So this is, if you remember the last slide, this was of type BC2 tilde. And then we have the quiver Q, which is 1, 2, 3, and a loop at every vertex. Well, the greatest common divisor of 1 and 2 is 1, so we only have a single arrow between any two vertices.
Excuse me,
Yes.
the f in the definition of the ideal after the exponentials of epsilons, they must be fgi, right?
Yes, so the one f is
Fji.
fij, and this one is, the other one is f. Yeah, this is a little bit
So it's
fji.
Oh yeah, and what's this alpha g?
This alpha, yeah, and the G, yeah, I didn't say where the indices run through. So the I and the J, they run through all vertices, and the G runs from 1 up to GJI. So just for every such arrow here, we want such a commutativity relation.
Thank you.
Yeah. Yeah, so that's the quiver in the example, and the ideal I is then given by, well, the symmetrizer. I didn't mention the symmetrizer here, but the minimal possible symmetrizer to choose is we take 1 here, 2 here, 2 here, and 4 here. So we get as our ideal of relations, it's generated by epsilon 1 to the 1, epsilon 2 squared, and epsilon 3 cubed. Then we have two commutativity relations for alpha 2, 1 and alpha 3, 2. And these are alpha 2, 1, epsilon 2 squared is equal to alpha 2, 1, epsilon 1. And the second commutativity relation is alpha 3, 2, epsilon 3 squared is equal to alpha 3, 2, epsilon 2. Yes. So that's it. And what we see here is that, well, we kill the loop epsilon 1. So we can actually forget about this loop and forget about this loop in the relations as well. And of course, since epsilon 1 is 0, also this first commutativity relation is just void. It doesn't tell us anything. So we can leave these commutativity relation out or these relations out. And often as soon as we have a value 1 of the symmetrizer, we just leave out this loop completely and forget about it because it makes notation a little bit easier then.
Sorry, so in this case, the fact that epsilon 1 is 0 would not imply that epsilon 2 square alpha 2, 1 is 0.
Well, it does imply it, but it is already 0 because we also kill epsilon 2 squared.
Ah, yes, of course. Cheers. Yes.
And this will immediately, I mean, as soon as we kill one loop, the other part of the commutativity relation also has to be 0 by the way these numbers are constructed.
Okay. Cheers.
Yes, and what's actually quite interesting to understand these algebras a little bit better is we can deform the relations. So what we can do is instead of killing epsilon I to the sigma I, we can say it is equal to t times the idempotent at I. Yeah, so instead of killing everything, it just multiplies, or the sigma ith power of epsilon I multiplies everything by a scalar t for some t in the complex numbers. We are working over an algebraically closed field of characteristic 0, so it's probably the complex numbers, but let's say k. And let's denote this ideal by it, and then we get actually a slightly deformed algebra ht for any complex number t. And as it turns out, this is for t non-zero, this is isomorphic to the path algebra of a quiver, of an unfolded quiver, which I call unfolded quiver. And this is for all t non-zero. So this helps very much. And only in the limit when t goes to 0, we obtain this GLS algebra. And what is the unfolded quiver in our example here? So in this example, the unfolded quiver is actually 1, 2, 2, 3, 3, 3, 3. And arrows go like this. So what you do is you basically at every vertex, you know that the loop epsilon acts by a non-zero, acts by a diagonalizable matrix whose eigenvalues are sigma ith roots of the non-zero value of t. So you can decompose it into eigenspaces and then obtain from there the unfolded quiver Q bar. So these deformed relations, epsilon I, sigma I, t, they allow you to decompose your vertices into the eigenspaces of epsilon. And then the commutativity relations, they dictate how the arrows are allowed to go in between these eigenspaces. So that way you obtain the unfolded quiver. And that's very helpful to understand the representation theory of GLS algebras, as we hopefully see in a couple of minutes. Okay, so are there any more questions about the definition of GLS algebras? Nope. Then let's proceed. Yeah, I prepared some more examples, but I think it might be more reasonable if you work through, if you come up with some value quiver your own on your nice sheet paper and then just calculate some GLS algebras. I think that's quite fun actually. Okay, so I turn immediately to varieties of GLS, of representations for the GLS algebras. So recall we had, and we from now on also will fix a valued quiver. And to this we associate the algebra H of gamma. So we will fix this also from now on, which is given as a bound quiver algebra. And we have seen if we now take a dimension vector, we get a variety of d-dimensional representations of H, which we denoted by rep of H d. And our goal was to understand representations of H generically. And the first step towards this this goal is a theorem of, or let's say the proposition of Geiß Leclerc Schröer from 2016, which says, let R be an element in the free monoid generated by the vertices of our valued quiver gamma 0. And we think of such elements as rank vectors. I will explain the terminology in a second. Then they consider a particular subset of representations. So the subset rep LF, LF stands for locally free representations of H with rank vector R, is defined as the set of representations V such that if I multiply with my standard idempotent coming from the bound quiver algebra description to V, so I consider the vector space associated to the vertex I of my quiver. So this should be a free module over the algebra EI. So this local algebra at the vertex I. And this actually has a very explicit description in our setting, namely, or for these GLS algebras, namely, this is just K epsilon I modulo epsilon I sigma I. Yeah, and we want the vector space associated to the vertex I to be a free K epsilon I modulo epsilon I sigma I module of rank Ri. And that's for every vertex in my valued quiver. Okay. And yeah, and this is where the terminology locally free comes from, because locally at every vertex, it's a free module. And that's also where the terminology rank vector comes from, because yeah, the entries of my rank vector, they really give me the rank of this module associated to the vertex I. Okay, and now Geiß Leclerc Schröer proved that this is actually equal, or has a homological description, namely this is equal to all representations such that the projective dimension of V is at most 1. So V as an H module. This is at most 1, and all of these are subsets of the representation variety of H with dimension vector sigma R, where this is the vector with entry sigma I times Ri. So that's an usual dimension vector. Okay, so they proved, first of all, this equality of sets already in an earlier paper. But then the main content of the proposition, or what I want to highlight, is that this is an open subset, and it is an irreducible subset of a very computable dimension, namely of dimension given by the dimension of the general linear group associated to the dimension vector D, minus an explicit quadratic form Q gamma applied to the rank vector R. And this Q gamma here, that's the well-known, or at least in Lie theory, well-known Tits form, which is given by the sum over all vertices in my valued quiver time the sum over sigma I times Ri minus the sum over all arrows in my valued quiver. So we think of them as being elements in the orientation. And then the sums are sigma I times nu ij times Ri times Rj. Yeah, so this generalizes the Tits form of an ordinary quiver to valued quivers. Okay, so that's that's a very fundamental statement about the geometry of the representation varieties of these GLS algebras. And from there we get some irreducible components, namely the irreducible components which we define as Z of R, which is just the closure of this open subset of locally free representations inside rep of HD.
Sorry, Calvin.
Okay.
So in particular, this Tits form has an upper bound depending on V. I mean, it's or it follows from the definitions. I mean that this is always positive, or at least
Not quite yet. I mean, yet right now it can be positive definite, positive semi-definite, or indefinite.
right.
For general valued quiver. And of course, intuition tells us from quivers that the definiteness of this quadratic form should tell us something about the representation. And the goal of it is to see that it tells you something about the geometry of the representation varieties.
Of course. But what I mean is that the value that you have for the Tits format V could never be bigger than the dimension of general linear group of D, right? I mean.
Yeah, exactly. You're right. Yes. Since the dimension cannot be negative, you're absolutely right. Upper bound, There's definitely an upper bound, but there does not have to be a lower bound.
Right.
Yeah, you're right. Yeah, nice observation, indeed. Okay. Good. So we have these irreducible components.
So the question is that is this something that a priori one could have guessed because of the definition of the Tits form, or
I think it should. Sorry, I actually made a typo in the definition. There should be an RI squared. I'm sorry. Otherwise, it's quadratic form. It should follow from the combinatorics.
All right.
It's not a corollary of. I mean, it is a corollary of the proposition, but that's.
But it's like.
I think it's a short calculation that this has an upper bound.
Okay. Cool. Thanks.
You're welcome. Thank you for the question. So yes, we have these irreducible components, and now let me state the main theorem. So I've at least made it through to my main theorem. So that's in part in an article from which appeared last August in the archive, but there's also a new part to it. Namely, theorem tells us now that this Tits form Q gamma is positive semi-definite. As a quadratic form, if and only if there exists some upper bound n such that for every rank vector, such that the irreducible component Z of R is generically indecomposable, meaning that the general element or the generic element, meaning that there's an open dense subset of the irreducible component Z of R such that all the elements are indecomposable. So this only applies to very particular rank vectors R. But whenever we have such a rank vector, then we can bound a number called the generic number of parameters of this irreducible component by big N. So this is the generic number of parameters. And it is defined as the minimum over all codimensions of orbits in the component Z of R. So we take the minimum over all representations in Z of R. So it really means that if you want to describe representations isomorphic to V, then the number of parameters you need to describe this representation is precisely given by this codimension, and then the generic number is by the minimal is the minimal such number. Okay, and this generic number of parameters is bounded by some constant n uniformly in all rank vectors such that the component is generically indecomposable if and only if the Tits form is positive semidefinite. Okay, and yeah, maybe let's have some remarks about this. So the first thing you should ask is, what does this say for symmetric valued quivers? So for valued quivers which actually do come from an ordinary quiver. So if gamma is symmetric, meaning that the symmetrizer is constantly 1 everywhere, yeah, so the valuation is already the same on the left and on the right of every arrow, then we have that Q gamma is positive semidefinite if and only if the algebra H of gamma, which in this case is just an ordinary path algebra, is representation tame. So that's by the beautiful representation trichotomy of quivers. And in particular for representation tame, well, yeah, almost by definition for a representation tame algebra, we have in indecomposable representations at most one free parameter. So we get that in this case, the upper bound n is certainly fulfilled by 1 already. But now well, maybe the drawback, or maybe actually the interesting thing now is that in general, if gamma is not symmetric, then H gamma is often representation wild. Even though Q gamma might still be positive semidefinite. Yeah, and as an example, you may look at the quiver of type BC tilde 1, so gamma being 1, 2, 1, 4, where the symmetrizer now is 1 and 4, then we have that H of gamma is 1, 2, and a loop at 2 epsilon, and this loop epsilon is killed after 4 steps. And this is representation wild. Even though the quadratic form for gamma is positive semi-definite. Okay, other questions about the formulation of the main theorem?
No, but I want to highlight once again this last observation you made. I mean, the key point in all this work is to restrict to this particular kind of representations, which are the locally free, right? I mean, in general, the representation theory of any H of gamma for every given gamma is far from
it's far from
realizable, but
even the locally free ones are not yet classified in any classical sense. So it's and I think it's really exciting that we have some class of representation wild algebras, but they somehow behave in a generically tame way if the quadratic is positive semi-definite.
And also that they're sort of almost hereditary in some sense, even the
yes, so they are very close to hereditary because they are degeneration hereditary algebras. And of course all the locally free representations have projective dimension at most 1, so they
Yeah, yeah.
also are pretty much hereditary.
Yeah. Sorry.
Yeah, and maybe in the remaining, what is it, 15 minutes, 10 minutes?
Yeah.
I will sketch the proof of this theorem. So there are, every math student should see that there are two directions to prove. So this divides the proof into two steps. So the first step is to prove that if Q gamma is positive semi-definite, then we have that that the generic number of parameters is bounded. And the second step is if Q gamma is indefinite, then the generic number of parameters is unbounded.
Could you recall, please, what it means to be positive semi-definite?
Yeah, so positive semi-definite. Oh. So this here means that Q of R is bigger or equal to 0 for all R in Z gamma 0. Oops.
Yes.
Gamma.
Yeah, thanks.
Yeah, okay, so that's positive semi-definite. Positive definite means strictly bigger than 0. And indefinite means there are values for which it's positive and there are values for which it's negative. And from the construction of the quadratic form, from the value quiver, it follows that we are always in one of these three cases: positive definite, semi-definite, or indefinite. Okay, so yeah, maybe let's say a few words about yeah, okay, how do we do this? Maybe yeah. So the main technique to prove this is via tau tilting theory, or actually a geometric generalization of tau tilting theory, namely so-called generically tau-reduced components, which were introduced by Geiß Leclerc Schröer. But maybe I will, due to time, lack of time, I might skip the introduction to generically tau-reduced components and go right away into the outline of the proof ideas for this implication, for the first step. Namely, for this, we use the theorem which appeared on the archive in last year. So that's again a theorem due to myself from 2023. And this is a generalization of a so-called Katz decomposition, which is very well known for ordinary quivers. So we assume that Q gamma is positive definite, and we let eta be in a particular or a very special rank vector, namely this is the null root or the primitive null root for Q gamma, which means that eta is minimal with Q gamma of eta being equal to 0. Yeah? Since we are positive semi-definite, that's the minimal value we can attain with our quadratic form, and we take some rank vector which attains this minimum of the quadratic form, and it turns out that this is actually a one-dimensional a one-dimensional subspace in this vector space generated by the vertices of our valued quiver, and so we can a minimal positive such value, and that's eta. That's the primitive null root. And then every other rank vector R can be decomposed into a sum R equal to m times eta plus some other rank vector S. Yeah, so m is a positive, a non-negative integer, and S is some other rank vector, such that the corresponding generically locally free component Z of R is equal to Z of eta, and then we take a direct sum m times, and then a direct sum with Z of S. So this means, what this equation means is that the generic element, or the generic locally free representation of rank vector R decomposes into a direct sum of locally free representations, of m locally free representations of rank vector eta, and one more locally free representation of rank vector S. So that's an analog of Cutts canonical decomposition for valued quivers with positive semi-definite Tits form. And moreover, we can say a little bit more about, or we not only a little bit, but quite a lot about these components, namely this the general element of the general locally free representation with rank vector S is isomorphic to one particular representation W, and this one, and that's where tau tilting theory enters the picture. This one is tau rigid. So the general locally free representation with rank vector S is isomorphic to a given tau rigid representation W with this rank vector. And on the other hand, the generic representation of locally free representation of rank vector eta is isomorphic to one of a very explicit family of representations V lambda, where lambda is some parameter in some n-dimensional space for some n. For some n greater or equal to 1. So we have a parameter here. And if the symmetrizer sigma is minimal, in the sense that you cannot divide all the entries of the symmetrizer to get a smaller symmetrizer, then the number of parameters is actually equal to 1 here. Yeah, and so that's the generalization of Cutts canonical decomposition for valued quivers with positive semi-definite Tits form. And what we get from there is and this essentially proves one direction of my main theorem from today, because we see that all the generically indecomposable locally free components are either orbit closures, so have 0 parameters, or they are given by only for one rank vector, namely the rank vector eta. We have a parameter family, and there it's just some fixed number of parameters n. Yeah, so we get from there that the number of parameters of these Z of let's say Z of X is bounded by this n here. This n here. Okay. Yeah, whenever for all X being some rank vector such that Z of X is generically indecomposable. Okay. Yeah, do I have 5 more minutes for the other direction? Yeah, okay. So this proves this direction, and now the more interesting direction is probably not the more interesting. This already involves many ideas from tau tilting theory and the geometry of modular representation varieties. But now maybe the more novel part is the part that for indefinite, the number of parameters is actually unbounded. And yeah, so this is proven as follows. One considers a actually very classical family of rank vectors, namely the fundamental sets, so-called fundamental set, which is always denoted by F. And that's defined to be the set of rank vectors such that the support of the rank vector, meaning the set of all vertices such that the rank vector is non-zero, which is a subset of gamma 0, is connected. So as a full sub-quiver of the valued quiver, it's connected. And if we consider R and take the symmetric bilinear form coming from the Tits form and apply EI, which is the standard basis vector of n gamma, then this should be smaller or equal to 0 for all I. So that's the definition of the fundamental set. And now we have the following lemma. Namely, if we take some element R, some rank vector in the fundamental set, and we assume that the Tits form associated to the valued quiver applied to R is negative, then this component, this generically locally free component with rank vector R, actually is already generically indecomposable. So that's the important lemma to make this direction work. And now we just use a combinatorial or number theoretic fact maybe, which says that for all n greater or equal to 0, there exists a rank vector in the fundamental set such that Q of R is smaller or equal to minus n. Yeah, so the quadratic form is already unbounded from below on this fundamental set. Okay, and with these two things, we can now conclude that the generic number of parameters of our generically locally free component with rank vector R, if we assume that R is in the fundamental set with negative Tits form, this is just by definition the minimum over all V in ZR over the codimensions of the orbits of V in ZR. But now we just, what is the codimension? That's just the dimension of the set of R minus the dimension of the orbit of R. The orbit of V, sorry. And this is the same. Now we can just compute dimensions. This is by the proposition I gave you in the beginning from Geiß Leclerc Schröer. The dimension of ZR is equal to the dimension of GL of sigma R minus Q gamma of R minus, and now the dimension of the orbit is given by the dimension of the general linear group, which acts transitively on the orbit, of course, minus the dimension of the endomorphism algebra of V, because the dimension of the orbit is given by the dimension of the transitively acting group minus the dimension of the stabilizer of the group action on the orbit, but the stabilizer is just the automorphisms of the representation V, and the automorphisms are dense in the endomorphisms of V, so the dimension of the automorphisms are equal to the dimension of the endomorphisms of V. So we get this as our dimension or codimension, and now we can cancel sigma R, the dimension of the general linear group, and finally obtain that this is the same as the minimum for all V over dimension of the endomorphisms of V minus Q gamma of R. But of course, I mean, the dimensions of the endomorphisms of V are, let's say, greater or equal to 0. So this is, all of this is greater or equal to Q gamma of R, which was by the observation before, greater or equal to N. So this is unbounded. Okay, so that concludes the direction, this direction of the main theorem, and then I'm done. Thank you very much.
Thank you very much, Calvin. Are there any questions or comments? I do have some. I mean, some of the comments I already made, right? But this is beautiful. Really, I mean, it's a beautiful theorem. I like it very much. And and I wanted to ask you again here. So, how you? I mean, do you construct explicitly the parameters for these generic postulations, or not necessarily? The lemma that you have.
In the lemma,
Yeah.
so the lemma here says that this is generically indecomposable, and it follows from there's no explicit construction of the elements there.
All
so
right.
I don't have an explicit construction of the generic elements in there. It follows from some general arguments about the behavior of the quadratic form,
Okay.
and some dimension counts.
Ah.
You basically count the dimension, so you assume it's not generically indecomposable. So then you would have a generic direct sum decomposition, but then the quadratic form evaluated at this sum decomposition of the rank vectors would the behavior of the quadratic form on the sum decomposition would imply that the dimension of this direct sum of two components is too small.
I see.
So,
Yeah.
so good that it's actually
Ah, I see.
decomposable.
That's very cool. Thank you very much. Any other?
Yeah.
I have,
Yeah.
well, it's about this symmetrizer that appears in the valid quiver. My question is if it's somehow related to symmetrizable matrices that appear in cluster algebras.
Yeah, absolutely. I mean, this was the main motivation for Geiß Leclerc Schröer to introduce these algebras. That this datum of a valued quiver I sketched in the beginning, this datum is actually better known under the name of having a Qatar matrix with a symmetrizer and an orientation. So this is equivalent data, and of course, what Geiß Leclerc Schröer tried to do is to relate their GLS algebras to the universal enveloping algebras of the corresponding Kac-Moody algebras. And then this was, of course, this whole theory of Kac-Moody algebras was one of the main motivations for cluster algebras. Yeah.
Oh, thank you. I see now. Yeah.
Yeah, thank you for the question.
Any further questions or comments?